Greetings, my name is Pedro Moreno and welcome to the Extra Points Activity video evidence from Practice 2 of the Advanced Electronics Laboratory, covering the operational amplifier in a summing amplifier configuration using both op-amp inputs, the inverting and the non-inverting. First, we start with the mathematical verification. For this circuit, the output voltage is determined by the algebraic sum of the signals applied to both the inverting and the non-inverting terminals. We can adjust the resistor values in our array, so we can independently scale the gain for each input before they are combined at the main op-amp, as shown in the formulas of the figure 1. To make this easier, we have fixed all the resistor values to 1 kΩ and we have added an extra inverting amplifier phase with a gain of 1 to the signals connected to the non-inverted input of our principal operational amplifier, so we can obtain a positive sum of the signals in the final result. Adjusting the formulas as shown in the figure 2, now we have that each input signal will have a gain of 1 and all of them will be positive values. Applying these principles, we modeled our circuit in Proteus simulation software. The simulation clearly demonstrated the theoretical behavior, showing how the multiple input signals combine to form a single amplified output wave. And before we move to the physical assembly. Here we have the practical circuit built on a protoboard. Initially, we monitored our input signals by connecting the 4 oscilloscope probes directly to the signal generators. It is important to highlight that because we are using 2 independent signal generators, there is a time offset between both generators, so we might have small variations in the output signal. We also need to adjust the phases to obtain the best synchronization of the input signals. Then, to observe the circuit's operation, we move the 4th oscilloscope probe from the signal generator input to the output of operational amplifier configuration. Now, we can see the signal on the oscilloscope represented by different colors, input 1 in yellow, input 2 in blue, and input 3 in magenta. On channel 4, in green, we now have the resulting output signal, which successfully reflects the mathematical sum of the inputs configured in our circuit. To clearly observe the summing effect in real time, we start changing the amplitude of input signals to 0 one by one. First, the blue signal drops to 0, and you can immediately see the green output signal decrease in amplitude, since it is now only summing the active waves. It is important to highlight that because of the offset between both generators, we may have small variations in the output signal. We repeat this by turning to 0 the other inputs one by one, and then the green output adjusts accordingly, effectively losing amplitude with each input signal amplitude change. All the theoretical framework, mathematical modeling, and circuit designs demonstrated today were referenced from the book Electronic Devices and Circuit Theory by Bolestad and Nashelski in the Spanish edition. Thank you for joining me in this analysis, and I will see you in the next laboratory report.